So today, because I have a hard cutoff, I'll try to go a little faster. So first, I'll just discuss the causality condition that I'm going to use today, and then from that causality condition, also show in the light cone limit, we get averaged null energy condition. In the Regge limit, I'll show that there is some universality at large n, and then I'll conclude. Because I don't have much time today, so today I'll try to state the causality condition in a way that I can use for both these cases. But before that, let me briefly review what I talked about in the last talk. So the stress tensor 3-point function in a CFT in 4D, it has 3 structures. So the tensor structure is fixed by conformal invariance, but there can be 3 independent coefficients. From causality, we showed that this has to be true. And we and David Poland's group, we derived this from causality in 2016. Then probably, I think after us, Komartgorsky, Zavieda, Parnachev, and Kulaksisi, they derived this from deep inelastic scattering, again in 2016. But these constraints, they are known long before that. So in 2008, Maldacena and Hoffman they derived this in 2008, starting from averaged null energy condition. I'll use the short form ANIC. So that made us wonder if we can actually derive average null energy condition from causality. Before I do that, let me state what null energy condition is. So average null energy condition, the statement is the following. This operator, let me call this E, where U is the null coordinate. So this is positive in any state. In gravity, this is actually very important because it's well known that matter that violates average null energy condition, that can be used to make time machine, and also you can violate second law. So it's at least from the gravity point of view, it's better be true. Even in gravity, there are other energy conditions. For example, strong energy condition, null, weak, dominant. But all of them have counterexamples. But average null energy conditions, it doesn't have any counterexample, so it might as well be true.
Why for gravity is the average important?
Average is not important, but like it's the weakest. Like if you impose null energy condition, that's stronger than this. So, and it's known that there can be violation. So even if you have like a weaker version, it can save.
So that the second law is correct even if the average null energy condition is.
Yes. Yeah. So there is.
Why is that?
there is a paper by Aaron Wolf where he claimed that this is the weakest version that
Ensures the second law.
yeah.
Okay.
But that proof I don't even think that incorporates all the most general condition like situations, but at least in some situations this can save you.
And so this in four-dimensional theory, this is three parameter set of conditions. This thing is labeled by 3-parameter set of light rays.
Mm-hmm. And I guess even more than that, because you can.
Oh, because you can choose the direction.
Yes, and also like you can just, this is an operator statement, so you can just like stick in any operator you want, and this should be true.
So this is meant to be an expectation value in an arbitrary state or even matrix elements, or what?
Basically, the statement is in any state, the expression value of this should be positive.
Why the integration along the null only? How to fix which line to integrate about?
No, you can pick any null, complete null direction.
That is only special.
Choose a ray.
Mm-hmm.
The U indices are contracted in the direction of that ray.
So there is a covariant version, but basically this is.
Every null, infinite null ray does it.
Staying at constant theta high.
Mm-hmm. And there is a proof of this from monotonicity of relative entropy by Faulkner, Lay, Parikar, and Wang, 2016, I think. Where they started from the condition that relative entropy should be it should be monotonic, and from there they derived this positivity condition. But there are some subtleties, because all this information theoretic inequalities, it's not very well understood if they are still valid in quantum field theories. But even without that, their derivation actually doesn't tell you what goes wrong. So basically, for example, you know that if this is violated in their case, that will show a violation of monotonicity of relative entropy, but it doesn't actually tell you what fundamentally goes wrong in the in that quantum field theory. And I'll argue that it's basically causality. Before I proceed, let me just state the causality condition again in a way that I can use for both these applications. Today, I'll use a setup like this. So this is spatial direction y. This is temporal direction t. This is null coordinate v and u. And I'll choose 4 points this way. So point 1 and a Rindler reflection of this point. So it should be somewhere here. Point, let me call this 1 prime, point 2, point 2 prime. So the reason I select my 4 points this way, because there is something called Rindler positivity of correlator. It's basically similar to what Cassini called wedge reflection positivity. So this is a paper by Cassini from 2011, and unfortunately it just has one citation, as I checked last time, but it gives you a Lorentzian correlator which is positive. Similar things is in the chaos bound paper by Maldacena, Shankar, and Stanford. The statement is the following. If I have an operator O1, this can have spin. In general, yeah, let me just give it some spin. The Rindler reflection, let me just define this operator first. this is at some t, y, x. So the Rindler reflection, which I'll denote by a bar, that's basically minus 1 to the power p, where p is the number of t and t plus y indices for dagger mu minus t star minus y x. So basically flip your t and y coordinates, and if your t is complex, just take the complex conjugation. So this is how you define a Rindler reflection. So then this correlator is positive.
It's just 180-degree turn in the ATY.
Yes. Not just, yeah, yes. So this correlator is positive. Just, and this is a Lorentzian correlator. Check the ordering. So it's basically you have the same ordering. It's not that you're reversing the ordering. So in other words, this is imaginary T1 less than.
The Rindler Hamilton is in Euclidean space. The Rindler Hamiltonian is rotations in the dy plane, right?
Mm-hmm.
So this is an operation by motion with the Rindler Hamiltonian by Euclidean time I.
Euclidean time pi.
Because the 180-degree rotation times complex conjugation.
Mm-hmm.
I'm trying to understand why this should be positive.
I can give you a cartoon if that helps.
Yeah, just some intuition.
Yeah. So it's basically, at least in some cases, you can just think of this as reflection positivity in some other quantization. Let me give you a cartoon that might help. Let me draw the. So this is my y direction. This is my t direction. Let me draw another plane, which is my tau direction.
So tau is Lorentzian and T is Euclidean.
Yes. So this is my tau direction. So I have point light cone. I have my points 1 here, point 1 prime. That's on this ty plane. And let me put this 2 and 2 prime in the Euclidean direction just to make sure that I have the right ordering. So I'm giving it a Euclidean time component just to set the ordering. So it's, let's say, somewhere here in this Euclidean plane. Let me put it here, just 2. And there should be.
Which is Euclidean time, tau or T?
Tau is Euclidean time. So, and let's 2 prime should be somewhere here.
So both your points have 0 or Lorentzian time.
Yes.
Yes.
So this Euclidean time basically fixes the ordering.
Yes.
Now what you can do, you can just, this is at Lorentzian time t. What you can do, you can just evolve this in time. So you can just write this as some smeared operator over here. In principle, you can do that. Similarly, you can do the same thing, but you can do it back in time. So you can just mirror this over y plane. Now, if you look at this in the tau y plane,
You've drawn a light cone structure?
yeah. So basically, I'm just like from this one, I'm just evolving this in forward in time.
In Euclidean time.
No, this is in Lorentzian time.
I'm not understanding your diagram. Is tau Euclidean or Lorentzian?
So okay, so this 1 and 1 prime, they are on the ty plane.
Ah, I see.
So they
That's
do-
right. Yes. Okay, fine.
So if I draw this in now tau y plane, so this is my tau direction, this is my y direction. So this is basically at y. So this is basically here at tau equals to 0. So this is basically just mirrored O1 and smeared 1 prime. And 2 and 2 prime, they are here.
Yes.
So now across y equals to 0, it's basically a reflection of each other. So it's basically this. So this is a basically reflection symmetric configuration across y equals to 0 plane. So it's basically one can. So this correlator that I wrote, it's not a norm if you quantize at tau equals to 0, but it's a norm if you quantize at y equals to 0 plane.
And okay, so let me just understand. So you had but these two, the 2 and 2 prime, their tau coordinate was not reflected. What you just said.
Yes, because tau is imaginary and you have a star.
So this condition is Euclidean or Lorentzian?
So this is Lorentzian. So this T is Lorentzian.
Ah,
Doesn't it be complex?
Hmm?
Because there are small I epsilon p.
Yes. So that's if you have I epsilon space, because of negative sign, you'll get one negative sign. Then because of the star, it basically gives the same Euclidean time.
I see.
So the advantage of this linear positivity is the following. So first of all, it doesn't require conformal invariance. This is true for.
So if we just take T to be
Mhm.
Euclidean time,
Uh-huh.
oh. So this would be true whether the time was Lorentzian or Euclidean.
Yes. Yeah. Yes. But inherently,
If Euclidean time is treated as as imaginary.
yes. Yeah.
So in Euclidean time, this is just simple reflection positivity around y.
If in Euclidean, so if this is fully Euclidean, yes, precisely.
So it's just the analytic continuation of that, right?
Yeah.
Can't I say that?
That's true.
But you have to do the right stars.
And yes, yeah. And also, like if you have indices, it's not tricky, but you have to be careful.
What is this -1 to the power p?
Oh, that's basically number of t and y indices of this. Because you are just switching t and y coordinates, it's basically that -1 to the power p because of that. And another advantage of this linear positivity is basically you're allowed to smear all these operators as long as you're. Yes.
So can you explain minus T star? What is that doing? So you're doing a T star and then you're taking minus.
Yeah, so it's basically.
That gives the Euclidean, the I epsilon part the same. And.
But the Lorentzian time it becomes negative of itself.
Lorentzian is negative.
So Euclidean part stays always the same, but Lorentzian part basically gets a negative sign.
So in pure Euclidean space, this is simply reflection positivity. Is this right?
Across y, yes, precisely.
Some analytic continuation of reflection positivity.
Okay, so now if I have a correlator like this, O bar psi is scalar. I'm going to study some properties of this correlator G. O can be any operator.
Sorry, just to go back to that comment of Shiraz. Now, so then P should count only the number of Y's, not the number of. Oh, I see. So when you go to this mixed, the complex T, then you also count. No,
So first, if T is fully Lorentzian, then I don't have this star.
No, but let's go to fully Euclidean.
fully, yeah, if it's fully Euclidean, basically,
Nothing is happening on the T slot.
yes,
Right?
yeah.
So then it should, this parity thing should count only the number of Y's.
But these are all Lorentzian indices.
No, but let's analytically continue.
Mhm.
So then, does that P count T as well?
Yes,
So
yes.
doesn't that violate reflection possibility? Because as Gautam said, nothing is happening in T. If you flip a sign in T, you get something negative.
I guess the difference is basically even if you start from Euclidean time, then basically you should analytically continue y, not tau, because your
The mu index, because of T goes to I, it will pick up a I, because of coordinate transformation.
mhm,
When you go from Lorentzian to Euclidean time,
uh-huh.
and then dagger will pick up a minus sign.
Yes, yeah, probably, yeah.
Maybe that's it.
So the dagger takes care of this.
Mhm.
Okay.
So you need the T.
Yeah, that you need for sure. Yes, yeah. Okay, so now just because this is a positive positivity of this kind of correlator, that basically gives you some that lets you define a positive inner product, and from that, what you can actually show, I'm not going to show it. It's just few steps. That real part of G, it is basically bounded by this. Okay. If I normalize everything by 2-point functions of O and psi, you can actually just show from Cauchy-Schwarz inequality that this is bounded by 1. This is exactly the same condition that we derived in the last talk. So this is a consequence of this Rindler positivity. I can go to the previous talk's computation, but the causality condition now becomes, if I write G as 1 plus delta G, the imaginary part of delta G, that should be positive. The reason is, let me give you a brief sketch why this is true. It's basically the same condition that I derived in the last talk. So let me draw a diagram.
You say you said this in the last talk, but I can't remember. What is the roughly the logic that tells you that this is less than 1?
Real G less than 1? It's basically because of Cauchy. I can just probably derive it. It's basically the statement that the second sheet correlator is bounded by the first sheet one. So
What sheets are we talking about here?
So this is basically whenever I'm writing a correlator like this, it's basically the orders are as written. So this is on the second sheet. This G is on the second sheet.
Now, I see. Sorry, this UV. I'm totally.
I can.
The times are these.
Okay, let me draw.
Lorentzian,
Yeah.
Euclidean, what's
No, now everything is Lorentzian.
Lorentzian and the
UV, let me draw UV, yes. That's going to be important. Let me just forget about O and O bar. My psi is somewhere here, and psi bar is somewhere here. Where the coordinate of this point is U, comma V, where UV are null coordinates, and this is minus U, minus V. And I'll take my U to be 1 over sigma and V to be minus eta times sigma, just a notation. So this is basically on the second.
O's are where?
O's can be anywhere, it doesn't matter. So this condition is, it basically tells you that because this is on the second sheet and this is basically.
I didn't understand the second sheet. And does that depend on whether what O's are?
They do. Let me put the O's here on the.
So which are the time-lag separated guys? Psi bar and O and psi and.
Yes. Yeah.
Psi bar and O and psi and.
Psi and psi bar.
Which is O bar?
O bar. This should be O bar. Which one I'm calling O and which one? This is O bar.
O bar, psi bar, O and psi.
Yes.
So the only question of relative ordering is between O and psi
Mm-hmm.
and O bar, psi bar.
Yes.
Now the way you've written it, O is after psi, so
Hmm.
that's flipped ordering.
Mm-hmm.
But and O bar is after. O bar is before.
So the positive order, the thing that's positive, that's basically O bar psi O psi, because
Where's psi bar there?
yeah, it's basically scalar. That's why yeah. So the positive order thing from linear positivity is basically this one, O psi bar O psi.
With time ordering would have had psi to the right of O
Mm-hmm.
and O bar to the right of psi bar. Both are flipped.
Both are flipped. Let me check.
It looks like third sheet, not second.
No, let me check. Okay, the way we have been thinking about it, basically first we write the thing that's positive from linear positivity, which is this correlator.
Yeah.
So then basically,
Actually, why is it that correlator rather than?
because like in the linear positivity, basically it's the order is order on the left and order on the right is the same. So that's the starting point. That's the any other correlator, that's basically an analytic continuation of this one, and because of the positivity of this correlator, basically you can only reduce it.
Okay.
So that's why this is basically if you normalize this by the 2-point function, this is basically 1.
Actually, many things I'm not understanding. Why is that one?
First, it's basically 1 if you just do the computation, like if you just try to compute this one. This is basically, let me say it correctly.
What does it mean that it's one? It's an independent position.
It's I don't know. It's not independent of position. It's basically the 2-point function.
No, I mean that has the same position dependence as 2-point functions.
Yes. Product of 2-point functions.
So only identity contributes.
Yes.
Why?
It's basically precisely the statement that you are not causing any branch cut.
When
Let-
you cross branch cut or not? I mean normally all operators cross.
Yeah, but okay. So yes. Okay, this is not one. Okay, yeah, I see. This is basically some function of epsilon and eta. So not epsilon, sorry, sigma and eta. So we'll either and this you can actually show that this function comes with positive power of eta and positive power of sigma. So for today, I'll either take eta to 0 or sigma to 0.
Eta to 0, sigma to 0. What is the
So basically, that means basically I'll take this to close to the light cone.
Okay.
So because it always comes with positive power of eta and sigma, in the light cone, when psi and psi bar they approach the light cone, basically it's basically there is a factorization basically.
There's factorization. So you're bringing, it's sort of you're doing O with O bar and psi with psi bar, that kind of OP.
Yes.
Even though, I see, that's allowed because psi and psi bar are coming near to each other because they're on the light.
Yes.
Okay, fine. And because the distance is so small, identity dominates.
Mhm.
That's what you're saying.
Yes. Yeah.
I understand. Fine. Okay, please go on. So this is one you say.
So that's how we get. That's basically this correlator is bounded by 1, and this one is basically an analytic continuation of that one.
Okay, this one's dominated by 1. So there's no Euclidean anything.
No, not it. No.
So you continue from here to there. Okay.
So basically, like, this is exactly what I talked about in the last talk, but this is just in terms of linear positivity. There is not, like, it's a very easy derivation. It's just linear positivity.
And I see. So I still didn't understand less than equal to what. You had 1 plus something.
Uh-huh.
You know that was less.
So okay, so this not less than, basically there can be some function epsilon which comes with positive power of eta and sigma. So whatever I'll say, that can have a correction in positive power of eta and sigma.
You're saying it's basically 1.
Yeah, that's the statement. So
At least this one, and then that reduces.
yes,
Okay, that is bounded more or less. I understand.
and from here you can go to this statement. That's just from the contour diagram that I draw in the last talk. So that you can draw a contour in the complex sigma plane. And this is basically telling you that actually this comes from the fact that G, the magnitude of G is less than 1, so that's basically it's bounded here by 1.
Where do you use positivity?
Positivity basically just the fact that from if I analytically continue from here to here, it will reduce.
Okay.
That's the only place.
Okay.
And I'll need this. Just if you remember that I had to derive a sum rule last time that says this. That says basically yeah, I can write a sum rule like this. An integral over this of 1 minus real part of G d sigma. I did the same thing in the last talk. So because of this positivity, I can get.
Even though you've done it in the last talk, I'm just going to try to understand it again. Sorry. So you on this contour, on that semicircle, things are bounded.
Yes.
Good. Then you want to know, and you know that it's analytic inside.
Yeah, I know that it's analytic inside.
Because of causality.
Yeah, causality, and there are many ways you can derive it. It's basically it's analytic inside. I can do this contour integral basically.
So this contour integral is the same as the down.
Yeah. Yes. So when I'm writing the imaginary delta, this is not actually right. Let me. So the delta G, it goes. Let me write an expansion. It's basically imaginary.
Delta G is the deviation of G.
Yeah, 1 plus delta. Yeah. So let me write an expansion because that's easier. It's generally go as this, negative power of sigma. So the right hand side, in the left hand side, I'll have an integral of delta G over the semicircle. This is sorry. The sigma real part of that, something like this. Now if you just plug this thing in.
Sorry, and what happened? Where did you get these reals from?
So that's basically I'm taking the real part of. So that's
you just take real.
Yeah. Fine. So what you can show that for, just if you just plug this thing in and take the real part, and you have to take few limits. There is R, and this R is small, things like that. What you can show that only the C1 contributes in the left hand side because you are taking the real part.
Sigma was what on this diagram? This is complex sigma plane?
Yeah, complex sigma plane. So they basically it's when it's 1 over sigma, basically then and only then it's real.
When it's 1 over sigma, only then is it real. So you're saying you just do the integral?
Yeah, it's just manipulation. You just plug this thing in, you can just show that C1 will only appear.
But this I should be able to see, right? So 1 over sigma to the power n.
Mm-hmm.
So So you just do the contour integral from
Yeah.
e to the power I n theta.
Mm-hmm.
So it's e to the power I n pi minus e to the power I n 0
Uh-huh.
divided by n.
Yes. Yeah.
And you're saying that that is n real only for n equals 1?
N equals to 1. Yeah.
Why? What about n equals 3?
So what will happen? I can just do the integral. Basically, at the end you'll have this. Let me do the integral. So you'll have something like this: I C n over r to the power n minus 1 I n minus 1 pi minus 1 real part of this.
Right. Now there's some odd even business.
Yeah, but that even so this quantity, if n is not equals to 1, it's either so this can be 0 or 1. This so because there is the I extra I over here, so it's always imaginary.
Wait, if n is equal to 1, what special thing happens?
So if n goes to 1,
Oh, so there's some limit.
yeah, yes, yeah, yeah. Because there will be one. It should be 1 plus I times n minus 1 to the pi. Then
I
there's,
see, I see.
it's basically it picks up C1.
I see. So,
So
same business about only, it's like half a pole being picked.
and
Half answer, only single pole configuration.
and this is actually very important because actually you can project to this way. You can just multiply by sigma square, sigma to the 4th here. You can just pick a particular power of sigma.
Fine.
So that actually tells you that imaginary delta G. So that's positive because from here you get basically C1 greater than 0. Furthermore, you can just project to different sigmas. You can actually show that this imaginary part of delta G, it cannot grow faster than 1 over sigma.
Just go a little slow. When you got real part of G, that isolated C1,
Yeah. And this part is positive already.
it's positive because real part of G is small?
Yeah, so that's basically this condition.
Yes.
So I have the condition that this is C1 is greater than 0. And you can actually, because I can project to other powers of sigma, it's basically the way we ruled out conserved current with spin greater than 2. That way you can actually basically rule out everything other than 1 over sigma.
And just to totally understand, you have this real part of G could have been 1 plus something.
So that's basically, yeah. So there can be corrections of the order of a positive power of sigma or eta.
Yes.
But this generally goes as 1 over sigma. So they will not be important.
Fine. Yes.
So the statement is, okay, let me just write down the statement, which is so the statement is, this is actually you get the same condition even from the chaos bound, that imaginary part of delta G, it cannot grow faster than 1 over sigma and it's positive. So this is what I'm going to use to derive. So this is my condition. Let me write it down somewhere.
How is this related to the chaos bound? Please?
It's basically they got the they actually also got the same.
Can you roughly say why this
Uh,
bounds this out of time correlator?
Basically, the statement of chaos bound is it's okay. So whenever I have a correlator G which has this particular form, 1 plus I some number, let me call it lambda, over sigma times a parameter, let me call it 1 over let me call it A, where A is positive but small.
So sigma is how near you are to that light cone?
Sigma is no, that's eta. Sigma is basically how far you're along this direction. So the statement of chaos bound or causality is the following. If anybody gives me a correlator of this form, 1 plus I times lambda, lambda is something I don't know, times a parameter A, which is very small, which is the smallest quantity in the theory, over 1 over sigma. So the property of this quantity is, as you take sigma to 0, this is growing, but still it's small because of the small parameter. So the chaos bound or causality that tells you whenever you have a correlator like this thing has to be positive.
And just, if it's hard, forget it, but can you
That probably I cannot do it on the board. But they are related. They are not very different. Okay, so what now I'll show you in the light cone limit. Okay, so my strategy is in the light cone limit eta going to 0. I'll show you this A is basically eta, and this lambda is expectation value of du du.
Excuse me.
Yes.
I'm wondering, is it clear expectation value that express time order?
Sorry.
Could not hear you.
The expression of G that is not time ordered. So
No, it's not. That's the point. Yeah. So G is basically exactly the way it's written. The operators are ordered exactly in the way they are written. Okay. Now, so the important observation that let me keep this. Let me write it somewhere. Imaginary delta G is greater than 0. So now the important observation is the following. So light cone limit is basically eta going to 0. Which is basically V going to 0. You can show the following. So this operator product expansion you can divide by the 2-point function. In this limit you can write in the following way. I can show you a derivation, but I don't think I have time. It's 1 minus Ct is the quantity that appears in the 2-point function of stress tensor, V u square minus u some kernel So this is the main observation that allowed us to relate causality and average energy condition. I can give you a brief derivation. It's basically, I can write this psi. I guess we talked about this in the last one. Because I'm taking the limit V is small, so this is given by u delta u to the power n times stress tensor, only the u component of that, and just from with some coefficient, and just from dimension analysis you can put some v u, I think u cubed times u v del minus L over 2. It's basically the same discussion we had in the last talk, why there is twist. And obviously there should be u square because it should contact with this, or u to the power L depending on the spin. And just plugging this thing in the 3-point function, you can find out all the coefficients Cn. Then you just, because you know all the Cn's, you just try to find out an integral expression of the same quantity. And it turned out that there is such an integral expression. You can just expand this in power of u, do the integral, and you can just check if if you are getting the same thing.
That's just an expansion. That's like a conformal block expansion there on the right hand side.
Yes, it's basically I'm just not conformal block expansion. It's,
Half
just,
of a conformal.
it's basically OP expansion where I'm keeping all the derivatives.
descendants.
Yes, all descendants. Yes.
Right. So this is sort of what you would need to, if you wanted to make the conformal block of psi with the T exchange.
This
from
is
this you can produce.
yeah, exactly. Yeah. So this is an operator expansion. I can just plug this thing in any correlator I want.
Yes.
And then the statement is that because I know all the CNs, I try to find out an integral expression, and there is one.
Okay. And you're using the fact that you're going to this light code limit and U.
Yeah. So basically, I'm using the fact that V is the smallest parameter there.
Yeah. Fine.
And then, if I take the limit,
Because of that, it's essentially one dimension.
or 2D, I guess.
What I mean is that there's only one derivative.
Yeah, one derivative. Yes. Yeah. And then, if I take the limit, u goes to infinity, which is sigma goes to 0, then I can forget about this kernel.
By the way,
Yes.
the positions of these operators and all, the remaining 2 points is just 0. X and Y.
All the other coordinates you mean? Yes, yeah, yes. So now if I take u to infinity, that gets rid of this kernel, and this integral starts from minus infinity to plus infinity. That's precisely the average null energy. Now I can just plug this thing in the 4-point function. I have which function? Yeah, I can just.
Sorry, what did you took the large U?
Yes. So I first take eta to 0, then sigma to 0. So this integral was from minus u to u. In that limit, it becomes minus infinity to plus infinity. So of course, I'm assuming all the other operators, they are basically at finite positions. They cannot be at infinity.
Okay, so your UV, the product UV was just eta.
Mm-hmm.
So that's eta to the power something.
Yes.
And U is, and you can now take the large U limit in that.
Mm-hmm.
Yeah, all right.
So pictorially, if you take 2 operators near to light-like separated, then the stress tensor is smeared and taken very far away along the light cone.
So this is the limit I'm taking. Yeah. First, I'm approaching this light cone. Then I'm taking this operator to infinity.
Yes. Then when you do that, when you produce the stress tensor,
Mm-hmm.
you say that stress tensor is equally smeared everywhere along the light line.
Yes.
Dominating. I mean, connecting the two. Is this unique to the stress tensor, or is it true?
No. This is true for any. I can just write this. Like I can write down the contribution of operator x.
It gets completely smeared along the light.
Yes.
Right. And in Euclidean space, this whole light ray is a point.
Yes.
It's
Yes.
just a statement that the operator is somewhere between psi and psi bar.
Mm-hmm.
But in Lorentzian space, it's a more fine statement.
Yes. Yeah. Mm-hmm. Now, if I can just plug this thing in the correlator G, O bar, psi, O bar, I can just plug this thing in.
That's totally remarkable. That you've got 2 operators very far away, but on the light line.
She was saying that they need a different zone for taking the Skype connection before 11:30. Then fine, you all of us.
Okay, so maybe 11:20 we can.
Okay. Then let me just.
Yeah, sure.
Okay.
Sorry. So you take 2 operators along light separated,
Mm-hmm.
and it's like there's a line inserted between them.
Mm-hmm.
It's almost incredible. Amazing.
And actually, we never even thought that something like that could actually exist.
I know it sounds.
We derived it in ADS safety first, and there it's obvious, kind of.
It's obvious.
Yeah, because it just computationally it's obvious. Like there you can just compute this 4-point function in the light cone limit. You see that this integral appears there, out of nowhere. But you can there you can actually like show it clearly.
It's a non-local kind of thing. I mean,
So in the bulk calculation, this integral appears how? I mean,
So basically, if you just try to compute this 4-point function and you take the light cone limit, what happens is the following. So basically, so you are computing this diagram, and you are taking the light cone limit. Let's say this is at light lag separated from this one. What happens is that in that limit, you can actually just show this is equivalent to taking the graviton to the boundary and integrating over some null direction. It's just computationally you can just show that.
It's an incredible statement. Oh, this sounds really interesting. Okay.
Okay, so let me not go into the details for this case. So now I can just plug this thing in here and I can just use this condition to show that this is a positive operator. So basically this thing is positive.
Yeah, the point is you plug in the psi and then O and O bar creating states.
So and O can be anything, primary, descendant, it doesn't matter. Yeah, yes, precisely. So now let me go to the second case, which is the Reggie limit, which is where, and there is one more statement. There is an generalization of this statement. That's basically at any even spin, find out the operator with lowest dimension. So that operator also satisfies this condition. It's basically just a generalization of this case. So at any even spin, the lowest dimension operator, it has to be positive.
This comes from different powers of that sigma.
Yeah. I can just project one of them, and there are some convexity relation that I can use, and this is true. And you can actually show that this is the strongest known condition in CFT. You can find out different constraints, and this constraint is stronger than any other known constraints.
So, for instance, in higher spin theories, in operators theories with the higher spin operators and nearly high spin operators, this gives positivity for those high spin charges.
Yeah. And another statement about this relation, that all we use is basically this light cone OPE. So this is a UV argument. So basically, this has to be true for any QFT with a interacting fixed point, UV fixed point. And this is similar to the argument made by Busso, Cassini, Fisher, and Maldacena in their Busso bound paper. But it's basically the statement is because it's true. Only thing I use is the light cone OP. This should be true for any QFT with interacting fixed point.
This integral, what is it measuring? Is it measuring radiation going out, or what? I mean, integral over this U thing.
Yes, it's basically null.
So it's not a normal kind of charge, which would have been like T naught not dx. It's not that kind of thing.
T naught not dx. No.
So what is it measuring really?
So one thing.
It looks like the energy radiation being measured across some light.
If you're far away from the from this operator, you can think of this basically it's measuring amount of energy deposited after a long time. If you're far away from this operator, that's basically the condition that Hoffman and Maldacena used in their paper. Basically, it's just kind of measuring the energy if you're far away.
It is measuring an energy. How?
It's basically like you can, if your insertion is at the center, and you're measuring this quantity and like far away from the center. So it's basically you can show that that this quantity, that T naught dt, this integral and this integral becomes almost the same at r going to infinity. Just so that's one reason why in the
Not T naught not dt. It should be T naught not dx.
sorry, this should be T naught n hat dt.
Fine.
But isn't this measuring a light?
But that how?
So this, if this operator is far away, it kind of looks like that, but that's probably. But this is even stronger than this condition.
Suppose you think of it as put that index up.
Which one?
Say we put one of the indices up.
This indices, I mean not this one.
Yeah, that
Okay.
one, let's say. TV. Would that make it look more like what you want?
It's basically.
TUP is what? It's H minus P or not? Sorry, I'm getting all confused. Sorry, we can
Yeah.
clarify this later because you don't have much time.
Okay, now let me take the Reggie limit.
Let me just tell you something I remember. This Lightful discussion, the Heisenberg discussion, the charge with all minus coordinates integrated over sigma minus. The current with all minus integrated over was a Lightful charge.
The light from charge. So there is some kind of Gauss law which measures. I see.
And it has to do with this flipping of Lightful.
Which one is
Up and above.
Okay, so because I have 10 minutes, let me just state the results and the most important part in the Reggie limit. So in the Reggie limit, it's not true that only the stress tensor can contribute. So again, I'll compute something like this.
What are you trying to prove now?
Now basically, I'm trying to prove that if I take the limit sigma going to 0, that in that limit basically, if you and I just keep the contribution of stress tensor, and I'll explain why whether it's reasonable or not. You can actually show that.
Oh, this is the thing, that your stress tensor block preserves causality.
Yes.
This is
Yeah. So basically, in 4 dimension, there are 2 central charges, A and C, and gravity. ADS CFT tells us that A has to be same as C. The question is if this is more universal, in the sense that is there a large class of large n theories which also should obey this condition.
I know it. Yeah.
Okay, so let me not go into the computation. Let me just tell you what we did. So we studied this correlator, stress tensor with some polarization, which is smeared.
More precisely, you're going to show that unless A is equal to C, this block violates causality.
Yes, yeah. So the important thing is, in our computation, the stress tensor is not exactly at this point. Basically, you are smearing over some. You are smearing using some Gaussian function. The reason is basically in the light cone limit, you can show that this kind of smearing that produces the strongest constraint. So I'm going to use the same kind of smearing, but now in the Reggie limit. Without going into detail, so in general, a lot of different operators can contribute to this 4-point function. But if I just keep the stress tensor block and demand that imaginary part of delta G is greater than 0, you can just find out delta G. Delta G goes as I over sigma, and it's actually kind of interesting that this sigma appears in the downstairs. Like it's not obvious from the beginning that this sigma will appear. If this sigma is not there, then there is no constraint.
So you're not going to the light cone because eta's fixed. You're just going far away.
You are going far away, yes.
So then, what's
So it's basically you're starting from here, you're approaching this point.
is your proper distance going to infinity or it's staying fixed?
It's just fixed, yes, yes. So it goes like this. T4, which is some combination that I'll write down, 1 minus eta to the power 5 plus I over sigma T2 and a function of radiation. This is a very non-trivial computation. It took us few days in Mathematica to do these integrals. So, okay, so this is the statement. If you just have the stress tensor and this thing has to be positive.
What is T4? What is T4?
Okay, I'm explaining. So, and you are taking the limit. This is in the limit. Okay, first sigma to 0, then eta goes to 1.
Goes to 1?
Yeah.
What is 1? What is 1?
1 means, okay, there are other dimensional full parameters. It's basically the bulk point limit, basically. So in terms of cross ratios, it's basically
Symmetric point.
yeah, z goes to z bar, where there is basically those Landau poles and Landau diagrams. So it's basically that limit. And basically from the gravity computation, we know that this is the limit where it goes to the deep in the bulk. So I'm doing the same thing, but in the CFT side. Okay, so the thing, this is a function of polarization. What you can show that you can pick and T4 and T2, they are some combination of NS, NF, and NP.
They're just numbers.
Yeah, yes. What you can show that for a particular polarization, this thing is positive. That means T4 has to be greater than or equal to 0. You can change the polarization, and for another polarization, you can actually show that this thing actually flips sign. So that means T4 for that other polarization has to be negative. The only way you can have a consistent solution is basically T4 has to be 0. The same thing happens for this term. You can just check that this flips signs if you change the polarization, and that tells you T2 has to be 0. And these two conditions together, if you just find out A and C, they are related to NS, NF, and NV. It's basically A equals to C. Now, one might ask if this is the right, just keeping the stress tensor is the right thing to do or not. So what are the other things that can contribute? First, okay, so I forgot to tell you a couple of things. So my assumptions are large N and a large gap.
Well, as far as so far I've just seen you say make some statement about a conformal law.
Yes, yes. So these two statements will be important. So by large gap, I mean
Only double traces contribute.
only double traces contribute. Yes, there can be operators with spin less than 2, but there is no operator above spin 2. And let's say I have one single trace operator at delta gap. Then one might ask how that changes this relation. I can just do that computation. It goes like this. And this is important because in the paper by Kamano, Edelstein, Maldacena, and Zaviadab, from the gravity arguments, they actually argue that this is how it should go. So now the second thing that you might think that contribute is the basically higher spin double trace operators.
Double trace operators of T.
Of T, yes. So let me write them as T, T, delta, and L greater than 2. But in the paper by Himskark, Penedones, Polchinski, Sally, they argued that at least in the Reggie limit, this will not contribute, just from crossing. And this is somewhat well known, and it's not that a non-trivial statement that anything that with L greater than 2, they will not contribute to the Reggie limit. So I can forget about these operators. Third is single trace low spin operators, L less than 2. You can show that this delta G, this goes as 1 over sigma to the power L minus 1. So anything with spin less than 2, they will be, in the limit sigma goes to 0, they will not be important. But the most important contribution thing that we couldn't rule out is this, Tt delta but L equals to 2. We know that they will contribute to the full correlator G. But that
infinite number of such operators.
yeah, they are yeah. You can show that if there is one of them, they cannot cure this problem. So if let's say, let me call this X, you can argue that if there is one of them, you will still have A equals to C. But the thing is that you can have multiple number of them. So let me. There are three possibilities. One is this contribute to the 4-point correlator, but because you are smearing, it might be possible that in the smeared correlator this doesn't contribute at all, or it's also possible that this contributes to the smeared correlator, but it can never cure the causality violating problem of stress tensor exchange. And the third option is basically this can actually cancel the causality violating contribution, and basically we cannot trust A equals to C. We don't have a proof that they will not contribute. Only thing that we can we have few guesses why they might not be important.
Are the blocks known?
No, yes, blocks are known, but if in this correlator they are known, TT, psi. Not known in this, you can like spend 2 days to compute one block, but in that way they are known.
For arbitrary delta.
Yes. Computationally, you have to fix delta first, and then you can do the computation, because like they are really messy.
You say you can do it on mathematics.
Yeah, basically even mathematics takes 2 days. So it's the argument is the following: because t, this 3-point function, and tx, they have entirely different structures. So even if you cancel the causality violating terms in this correlator, so that basically that will fix all the OPs and everything of all the x's. Then if you compute t, which we don't have, we just have some estimates how it should go. It should go as some. It will have this kind of structure.
What was psi, by the way?
Psi is scalars. So basically we use that to derive A equals to C.
I see. But what if there's no scalar? Pure gravity.
This scalar can be like, probably I can have one scalar set spin 0.
Trace, could it be a double trace operator? It could be anything.
It can be any primary. Yeah, it doesn't matter. Yes.
Yeah.
So this has this structure roughly, because since we don't have a result, it's something we estimated from few terms. But the thing is that this is from stress tensor exchange. If I have an exchange, there is no way you can generate this term. Basically, just because they have different structures, you can only generate these two terms. So it looks like even if you cure causality violation of this term, probably that can never cure the causality violation of TT. And in fact, these coefficients, they depend on where the other 2 points are. So it might make it worse. And
now, why isn't the same true for higher spin exchange?
so that's what I'm saying. This is for higher spin. Higher spin exchange doesn't have this. Higher spin, you mean L equals to L greater than 2?
I mean, yeah, just a single trace with a bunch of single traces with L greater than 2 can cure the problem, right?
No, cannot. Basically, just this statement that they do not contribute in the Reggie limit.
You're talking about the double trace operator.
So single trace.
Single trace with L greater than 2, an infinite tower of single traces with L greater than 2 can cure the problem.
But because I'm assuming that there's a gap.
I understand, but I'm trying to understand just technically.
Oh, if you don't have that gap, you mean?
Yeah. So suppose we didn't have the gap.
Yeah. Then
there are ways of curing the problem.
yes, precisely. Yes.
So one should try to prove something. You know, the kind of thing you're saying that if it's cured in one place, it won't be cured in another. You might also suspect that was also true for a bunch of an infinite set of.
But for that you have to check the structure of this, and I don't know if the structures are the same, and they are basically very messy. Like I can give you one more reason why it might be true, and this is somewhat convincing, but it uses gravity. So this 4-point function TT psi. The gravity side, it's basically this computation.
Right.
Then I forgot to mention psi. We're assuming psi is very heavy, just to ignore psi double trace operators. So if that's the case, in this diagram, this part, basically this integral is over full space-time. If that's heavy, you can just replace this by the geodesic.
Yeah.
Now, we didn't check this precisely because it's not easy to check. The smearing that we are doing, it's kind of what Hoffman and Maldacena did in their paper, and just in certain limit, it looks like that smearing is basically putting this part of the diagram also on a geodesic. So now this is a geodesic Witten diagram. And we know that this is basically just the stress tensor exchange block. So it's very possible that this smearing, that basically takes care of all the other operators, and you're only left with stress tensor exchange. But again, this is not fair to use holography to argue this, because that's what our goal was, just to show that certain theories behave like gravitational theories. But still, this was the motivation.
Well, sorry, one more question. So Lorentzian and company had this argument in the bulk.
Yes, yeah.
Is it difficult just to imitate that argument of the bulk?
Basically, that's what I said. It's basically that's the result of their argument. They also showed that, or they said that the causality violating problem in the bulk, they cannot be cured by adding massive spin to
I
particles.
understand this is the same result, but why can't you imitate the argument? You look like you have a different. For instance, they were able to argue it without further assumptions, right?
Mm-hmm.
You needed to exclude the double traces and so on. Why can't? Is there some barrier to just?
Yes, there is one problem.
What is the barrier?
So basically, what they did is basically, we don't know of a particular CFT 4-point function, the answer of which is basically the bulk computation. So they have some bulk computation, but that doesn't map into some CFT computation exactly. So that's what we are trying to figure out right now. That we want to start with a correlator, the final result of which is basically 1 plus the thing that they got.
So something that computes basically the S matrix, right?
Yeah. So basically, that we don't have yet. I think I should stop here.